All right, today's lesson is on permutations and combinations. Before we do this, though, we want to talk about what factorials are, and then we'll discuss permutations and combinations. All right, so a factorial, and you may have seen this before, of a number is the product of all the whole numbers from the number down to 1. The factorial of 0 is defined to be 1. So let's look at an example. 5 factorial means 5 times 4 times 3 times 2 times 1, which if you multiply that all together is 120. And that is read 5 factorial. And it says the factorial of 0 is defined to be 1. Why? All right, I'm going to show you this. 1 factorial will be 1. 2 factorial will be 2 times 1. So you can see the pattern here. 3 factorial, 3 times 2 times 1, which is 6. 4 factorial, 4 times 3 times 2 times 1, which is 24. So any number with a factorial, like if you put 7 factorial or 10 factorial, whatever number you put in for n, it could be that number times the next number behind it, the next number lower than that, times, and keep on going until you get to 3 times 2 times 1, and so on. So if that's the case, then you could also express a factorial at n factorial as n times n minus 1 factorial. For example, if you look over here, if we were doing 3 factorial, we could actually call that 3 times 2 factorial, because 2 times 1 is 2 factorial. Or we could express 4 factorial as 4 times, and then these 3 numbers represent 3 factorial. And if we do that, then when we have n equals 1, and we put 1 in for n, that would be 1 factorial would equal 1 times the next one down, which would be 1 minus 1, or 0 factorial. So if we have 0 factorial, then that means that 1 factorial has to equal 1, and we already know that. So then 1 times 0 factorial has to be 0 factorial, which would have to be 1 to get 0 factorial back again. Now, if that makes no sense to you, I'm sorry, but I just felt like I needed to show you that. But this is basically a way to show that 0 factorial is 1. If you do it on your calculator and punch in 0 and then the factorial key, you will get 1. So 0 factorial is 1. All right, so if you're to evaluate 10 factorial, then you could actually punch in your calculator 10 factorial and you will get 3,628,800. But there is the list of factors you would need. If you did 7 factorial divided by 5 factorial, that's going to be 7 times 6 times 5 times 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. Well, the 5 times 4 times 3 times 2 times 1 is the same in the numerator and denominator, so you could cancel all of those common factors. And when you do that, you're just left with 7 times 6 is 42. If you did 9 factorial over 8 minus 2 factorial, that would really be 9 factorial over 6 factorial. And then the 6 factorial would be up here with the 9 factorial if you wrote it 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And again, we can factor out all of these numbers, which is the same thing as 6 factorial. So those divide out and give you a 1, and you're left with 9 times 8 is 7. 9 times 8 times 7. 72 times 7 is 504. All right, so now you need that in order to do permutations and combinations, and you're going to practice those tomorrow in class. So now let's look at the definition of a permutation. It is an arrangement of things in a certain order. So order is important. All right. So if no letter can be used more than once, there are 6 permutations of the first 3 letters of the alphabet, ABC. So you can arrange them in these different ways. So if we look at that as a tree diagram, I call it a modified tree diagram because it's not exactly the way we see it normally. So if you look at my tree diagram here, you're going to see that if you can't use each letter more than once, that's going to be A times B times, or I'm sorry, not A times B times C, but A, B, and C would be the first letter of the three-letter permutation. And then if you can't use A again, then in the next row, it would just be B times C because A can't be used again. Same thing here, B, there'd be A times C, and then with C, there'd be A times B. So when you get to the last row to do the last in the three-letter series, the only thing left would be AB, would be C there. For AC, the only thing left, if you don't repeat, is B. And same thing here, BCA and BAC, and CAB and CBA. So there's your list of permutations. And that is, whoops, let me show you something else real quick. Okay, there's 6 of them. And that's really the multiplication, I'm sorry, the fundamental counting principle, sorry, which would be 3 times 2 is 6, and then 6 times 1 is 6. So there's your 6 different ways that could happen. All right, so when we look at it as a permutation, if you're going to do 3 things and none of the letters can be used more than once, order is important, then the first letter, there's 3 of them, 3 choices. Then the second letter, there's only 2 choices left. The third one, there's only 1 choice left, just like I did on this tree diagram. So if you multiply those together, 3 times 2 times 1, you get 6. But that is a factorial there. That could be written as 3 factorial because 3 times 2 times 1. All right, so if that's the case, then if no letter can be used more than once, there are 60 permutations for the first 5 letters of the alphabet when taken 3 at a time. So it says, you know, A, B, E, it gives you all these, and it says, and so on. Here is what the tree diagram of that would look like. So if you're going to take 5 letters 3 at a time, the first 5 letters could be A, B, C, D, E, and order matters. So then when you go down to the next row, there's only 4 choices. So the A drops out of the first, and you just have B, C, D, E. It could be with A, and so on. Then when you go down to the next row, for the third letter, there's only 3 choices left. All right? So you can see all the 60 choices there. There's 12 in each group, 12 in this group, 12 there, 12, 12, and 12. And you could list them all, but you can see them all here if you trace A, B, C, A, B, D, A, B, E, and so on. Now, that means if there's 60, that would be the same thing as doing the fundamental counting principle. The first row, there's 5 choices. Second row, there's 4 choices. Third row, there's 3 choices. And 5 times 4 times 3 is 60 permutations. Now, the way that's written is 5, the permutations, 5 things taken 3 at a time. And notice the 5 things would be the 5 factorial over, if you take 5 minus 3, that would be 2, and that's over 2 factorial. And the reason that works is because if you take 5 factorial and you divide it by 2 factorial, these 2 numbers are the 2 factorial, so you can cancel the common factors, and you're left with 5 times 4 times 3, which is 20 times 3, which is 60. And that works every time. So that's for permutations. And again, first letter, there's 5 choices. Second letter, there was 4. Third letter, there's 3, because order is important. So once you use one letter, you can't use it again. And 5 times 4 times 3 is 60 permutations. And so this is what we had, 5 times 4 times 3, which would really be 5 factorial over 2 factorial, and then the 2 factorial in the numerator and denominator cancel, and you're left with 5 factorial over 2 factorial. So here is a formula that you always use for permutations. If order is important and you're not going to repeat a letter, then it'd be the well, and this is not just with letters, we'll do other examples, but that would be the permutation of however many things, n things taken r at a time. The one we just did was five things taken 3 at a time. But that will always be n factorial over, then subtract the n and the r, get that difference, so you have to put it in parentheses, and then take that factorial. Now remember, we know by definition 0 factorial is equal to 1. All right, so if we go back to slide 3, where we had 3 choices times 2 choices times 1 choice, like this, okay, then the product can be written as a factorial, 3 times 2 times 1, which is 6, or that could be the permutation of 3 things taken 3 at a time, which is just filling in up here. 3 things taken 3 at a time was that particular example. So if we write it like this, that's going to be, if you recall, okay, n factorial, so that's going to be 3 factorial over 3 minus 3 factorial. And 3 minus 3 factorial is 1. So that's just going to be 3 times 2 times 1, like we said here. All right, so now if we look at some examples, there are 7 soup cans in the pantry. Find the number of orders in which all 7 soup cans can be arranged on the shelf. So order matters. So once you arrange one, it can't be there in the next position or any of the other positions. So that's going to be a permutation of 7 things taken 7 at a time. So that's going to be 7 factorial over 7 minus 7 factorial, just using the formula, which is 7 factorial over 0 factorial, which 0 factorial is 1. So you're just actually taking 7 factorial, which is 5,040 different arrangements. Okay, the next one, now what if there's 7 soup cans in the pantry, but the shelf only has enough room for 4 cans? Find the number of ways 4 of the 7 cans could be arranged. So you got 7 to deal with, but you only have 4 spaces. How many different ways can you do that? Well, that'll be the permutation of 7 things taken 4 at a time. So that's going to be 7 factorial over 7 minus 4 factorial, in parentheses, the quantity 7 minus 4. So that'll be 7 factorial over 3 factorial. But the 3 factorial can be canceled out of here, and here's the 3 factorial in the numerator. So those can be divided out. And you're just left with 7 times 6 times 5 times 4, which is 840. So 840 ways those cans, 7 cans arranged in 4 different arrangements. Okay, so what's a combination? Well, a combination is a selection of things in any order. Order is not important. So if no letter is used more than once, there is only one combination of the first 3 letters of the alphabet. ABC, ACB, BAC, BCA, CAB, and CBA are all considered really the same thing because order is not important. Once you get these 3 letters, doesn't matter what order you have them in, that counts as one combination. So combination order does not matter. Okay, so let's say if no letter is used more than once, there are 10 combinations of the first 5 letters of the alphabet when taken 3 at a time. So 5 things taken 3 at a time, but we're looking at combinations where order is not important. So let's look at a list of permutation and permutations, and let's go back and look at this tree diagram again. Okay, if we look at the permutations, remember there were 60, but order was important there. So if you had ABC, that counted as 1, and so did ACB. But those are considered the same thing in combinations. So if you have ACB or ABC, here then you could have BAC or BCA, and that wouldn't count, and CAB and CBA. And the other ones, they've got a D and an E in them, so those wouldn't work. All right, but when you do that, there won't be 60 because you have to take out all the ones that are alike, that have the same order. So here's all the 60. Now when you look at these that's the 60 permutations where order is important. But these are being grouped so that you can see that this group can only count as one group, and it's the arrangement of A, B, and C. This can only be the second group, which would be A, B, D. This is the third group. All of your arrangements of A, B, E can only be counted once. Same thing with these and all the way down the line. So here are your 10 different combinations of 5 things taken 5 things taken 3 at a time. Okay, but there are repeats because order is not important. So the numerator here, this is the permutation, the permutation of n things taken r at a time, which comes from this. There's our 60 things. That's our permutation. Okay? Well, if you take these 60 and divide them into groups of 6, that's like dividing it by 6, so the answer then would be 10. So what we do for a combination is we take the permutation and we divide it by a special number. And you get that special number by doing r factorial. Well, remember this was 3. R is 3. Well, 3 factorial is 3 times 2 times 1, which is 6. So now the permutation of n things taken r at a time, which is 60, divided by this r factorial, which is 6, will give you the 10. And this works every time. So our combinations formula is going to be the combination of n things taken r at a time, where order is not important. Means you're going to take the permutation where order is important of n things taken r at a time and divide it by the factorial of the r. So here is then what that looks like. This part is the permutation, the n factorial over the quantity n minus r factorial, if you recall that from the other formula. And then you also have to divide that by r factorial, which is right here. So let's do a couple examples. Okay, Harry wants to join a DVD club that offers a choice of 12 new DVDs each month. Okay, now when he buys those DVDs, order's not important how they come to him. Doesn't matter if they come, what stack, he's got the 4 DVDs, so order's not important on how he gets them. So what we want to know is there's 12 new ones, and he wants to buy 4. So find the number of different sets he can buy. So we're going to look at the combination, because order's not important, of 12 things taken 4 at a time. So that's going to be the permutation of 12 things taken 4 at a time. There's that part. Divided by this r right here, factorial. So that's going to be 12 factorial over 4 factorial times 8 factorial. So when we look at that, there's 12 factorial multiplied all the way up. Here's the 4 factorial and the 8. Well, why don't we divide out the 8 factorial from the numerator first? There they go. And those are all considered 1s now. When you multiply by 1, you just have this left. Now, the 4 times 3, we can divide out with a 12. And then this 2, which didn't get done, but if you divide this 2 out here, you can divide it out here, and so you have a 5. So actually you have 5 times 11 times 9. And 5 times 11 times 9 is 495 combinations. So Harry can buy 495 different sets of the 4 DVDs. Just depends on which ones he wants. All right, so B is if Harry wants to buy 11 DVDs, find the number of different sets of 11 DVDs he can buy. So now instead of buying 4, he's going to buy 11 of the 12. So that's going to be the combination of 12 things taken 11 at a time. So that would be 12 factorial over 12, the quantity 12 minus 1 factorial, which is the permutation of 12 things taken 11 at a time. And then we got to divide it by the r factorial, which is 11 factorial. So now we're just left with this 11 factorial divide out of here. That'll be like 12 times 11 factorial, so those will divide out. And then you have a 1 factorial, which is 1, so the answer is just going to be 12. Because all those are going to cancel out, and 1 factorial is 1. So do you have to write all this out and cancel these every time? No. You could just divide out the 11 factorial out of here, so you only have the factor of 12 left, and then divide the 11 factorial out of here. You don't have to write all this out. All right, so tomorrow you're going to come in and do this. I know it's going to be, you've got a lot of information there. Don't get overwhelmed. When you come in tomorrow, we're going to just work on factorials for a little bit and practice those, and then we'll look at combinations and permutations. So just come in with your notes and be ready to go. And one thing you could do is you could let's see, let's have you, if you watch the video, and please don't tell anybody, you're going to go get a pen out of the calculator pack, and you're just going to lay it on the help desk. Have a good evening.